Welcome to the deep dive. We're here to sift through a whole lot of information and pull out the essentials you really need. Today, we're tackling the role of the .NET architect. It's complex, super important, and, always changing. We've gathered insights from, well, everywhere foundational code stuff right up to the latest cloud patterns. The goal, give you a clear path to understanding this vital role.
That's the plan. Being a well-informed .NET architect isn't just about memorizing definitions. It's more about pulling together different strands of info, seeing the underlying patterns and connecting the dots across all these different areas. So yeah, our mission here is to help you see that big, complex picture clearly.
Okay, let's start right at the beginning then. What exactly is a .NET architect? What do they do?
Our sources say they design end-to-end architecture, ensure scalability, maintainability, performance, the drill, guide development teams, and align technical solutions with business goals. It sounds, well, less like just coding and more strategic, almost visionary. Exactly. They're the technical leaders thinking strategically. And, like any architect building a house, they rely on solid foundations. For a .NET architect, that foundation really starts with object-oriented programming, OOP.
OOP, right. Seems basic, but you're saying it's still critical.
Absolutely critical. It might sound old school, but what's really fascinating is how those core pillars, encapsulation, abstraction, inheritance, polymorphism, they're still the bedrock. Getting these truly right, not just knowing the definition, saves so much pain later. Take encapsulation. It's not just private fields right. It's about carefully controlling access to an object's internal state. Super important for predictable code.
That's a great point. It's the application that matters. And building on OOP, we get to the solid principles. These feel like the next layer up the guidelines for building systems that don't break easily, that you can actually change later.
They absolutely are. Think of them as like guardrails for design. Keeps you out of trouble.
Yeah.
First up, SRP, single responsibility principle.
The one-job rule.
Sort of, but it's more precise. A class should have only one reason to change. That's subtle and often harder than it sounds when features pile up.
Okay, one reason to change. Makes sense. What's next?
OCP, open-close principle. Open for extension, close for modification.
Yeah.
Basically, add new stuff without messing with the old working code. Usually means using interfaces, abstract classes, and that kind of thing.
Right, so you extend, you don't rewrite.
Exactly. Then LSP, Liskov substitution principle. This one trips people up sometimes. It says subtypes should work seamlessly in place of their base types, like swapping a basic light switch for a smart one.
Okay.
You still expect it to turn the light on or off, right? Even with extra features. If the smart switch only dimmed, breaking the basic on-off contract, that's an LSP violation. It changed the core expectation.
Ah, got it. So the substitution shouldn't break things.
Precisely.
Yeah.
Then ISP, interface segregation principle. Keep interfaces small and focused. Don't force classes to implement methods they don't actually use. Smaller interfaces are better.
Less bloat.
Yep. And finally, DIP, dependency inversion principle. This is a big one. A real mindset shift. High-level parts of your system should depend on abstractions, like interfaces, not on concrete low-level details.
So it's about decoupling.
Totally. It's what lets you swap out, say, your database or an external service later without a massive rewrite. Makes the system adaptable. You need that flexibility.
Okay, those are the foundational principles, but then architects have to think bigger picture, right? The overall structure. And that often leads to the big debate. Monolith versus microservices. How do you even start making that choice?
Yeah, this is where strategy really kicks in. A monolith is, well, one big, tightly knit application. Microservices, though, are, like our sources say, small, loosely coupled services, each responsible for a specific business capability.
So lots of little pieces instead of one big one.
Exactly. And the choice isn't just technical. It often mirrors how the business or teams are structured. Microservices promise things like independent deployment, better fault isolation, scaling specific parts.
Sounds great, but what are the catches?
Oh, there are catches, big ones. Decentralized data management is a major hurdle. You often have to deal with eventual consistency.
Which means data might not be perfectly in sync across all services immediately.
Right. That's a tough concept if you're used to traditional databases. And you absolutely need solid strategies for things like distributed logging and tracing to figure out what went wrong when it does. It gets complex fast.
So if these microservices are independent, how do they talk to each other without creating a tangled mess?
Good question. That's where event-driven architecture, or EDA, often comes in. It's a different way of thinking about communication. Instead of services calling each other directly, they communicate through events.
Events, like notifications.
Pretty much. An event is just a notification that a change in state has occurred.
Mm-hmm.
Something happened. Services publish these events to an event broker. Think of it like a central message board. Other services can then subscribe to the events they care about.
So they're decoupled. Service A doesn't need to know about Service B directly.
Exactly. That loose coupling gives you huge benefits in scalability and flexibility. Services react to events rather than waiting for replies. It enables real-time processing, too. Very different from the old request-response model.
Okay, EDA makes sense for decoupling. Then we hear about even more advanced patterns like CQRS and event sourcing. How do they fit in?
Right. These often pair well with EDA, especially in complex systems.
Huh.
CQRS stands for Command Query Responsibility Segregation.
Okay, break that down.
It basically separates the read and update operations. You have one model for handling commands, things that change state, like placing an order, and a completely separate model, often optimized differently, for handling queries just reading data, like displaying products.
So you optimize reads and writes independently.
Precisely. Maybe use different databases even. Then there's event sourcing. This one's really interesting. Instead of storing the current state of something, you store the sequence of events that led to that state.
Like a transaction log.
Kind of, yeah. But it's the primary source of truth. The big advantage is it enables replay and audit. You have a perfect unchangeable history. Combining CQRS and event sourcing gives you powerful ways to manage data in distributed systems, but yeah, it adds complexity. It's a different way to think.
Right. Let's shift gears a bit, moving from high-level architecture to the nuts and bolts of building .NET apps. Dependency injection seems fundamental. Why is that so crucial for an architect to grasp?
DI, yeah. It's foundational for modern .NET because it promotes that loose coupling we talked about, makes code testable, maintainable, easier to change. And ASP.NET Core is just built in. You register your services in a container.
And those lifetimes are important, right? Singleton, scoped, transient.
Absolutely critical. Get the lifetime wrong, and you can have subtle bugs or performance issues. Singleton is one instance for the whole app. Good for like logging services or configuration. Scoped is one instance per web request, perfect for things like a database context. And transient is a new one every single time it's asked for. Good for lightweight, stateless helper services. Choosing correctly matters.
Makes sense. Now, performance. Huge deal today. Async and await. How do they help build scalable apps?
Async await is all about not blocking threads, especially during I/O operations, waiting for a database, a network call, reading a file.
Stuff that takes time but doesn't need the CPU.
Exactly. Instead of the thread just sitting there waiting, await lets the thread go back to the pool to handle other requests. When the I/O finishes, the work picks up where it left off, maybe on a different thread. It's like that waiter analogy. They take your order, then serve others while your food cooks.
So you handle way more requests with fewer threads.
That's the key to scalability. Much more efficient use of resources.
Okay, that's scalability through non-blocking I/O. But what about raw speed and memory? Especially in really demanding situations. We hear about SPANT, memory T, array pool T. What's the deal there?
Now we're getting into the deep optimization territory. These can make a massive difference in high-performance code. SPANT is fascinating. It's a stack-only type representing a contiguous region of memory. Stack-only is key.
Meaning no garbage collector pressure.
Exactly. It avoids allocations on the heap, which is huge for performance when you're, say, parsing lots of data or working with raw memory buffers.
But you can't use it with async await, right?
Because it lives on the stack, its lifetime is tied to that specific method call. And await might resume on a different threads, losing the stack context. That's where memory T comes in. It's similar but heap allocated, so you can store it, pass it around, and use it across await points. It's for those async high-performance buffer scenarios.
Okay, so span for synchronous, memory for asynchronous high-perf buffer work, and await pool.
Array pooled is about reusing large arrays. Instead of constantly creating big arrays and making the garbage collector clean them up, you borrow them from a pool and return them when done. It drastically reduces GC pressure and improves throughput in scenarios that need lots of temporary large arrays. Less garbage collection means faster applications.
Right, okay. Let's talk data access, always a big topic. EF Core versus Dapper. When does an architect lean one way or the other?
It's that classic trade-off conversation again. Entity Framework Core is powerful, feature-rich, great for complex domain models, change tracking, and if you love writing queries with LINQ, it accelerates development, especially initially.
So more features, potentially quicker to get started for complex stuff.
Generally, yes. But Dapper is all about speed and control. It's a micro ORM. Very fast, lightweight.
Hmm.
You write the SQL yourself, mostly. It's excellent for performance-sensitive applications or simple data access and microservices where you want minimal overhead.
So EF Core for rich features and rapid dev, Dapper for raw speed, and SQL control.
That's a good summary. And beyond relational, there's the whole NoSQL world too, right?
Yeah, MongoDB, Redis, Cosmos DB.
Right. And again, it's about picking the right tool. MongoDB is great for flexible, schemaless document data. Evolves easily. Cosmos DB is Azure's beast for global distribution, multi-model support, high availability. And Redis. Well, Redis is just incredibly useful. It's that super fast in-memory key value store.
For caching.
Definitely caching, output caching, session state, but also distributed locks, message brokering, anything needing sub-millisecond latency. It's often the speed layer in front of a slower database.
Makes sense. Okay, shifting focus again to getting the software out the door. DevOps, CI/CD pipelines. Why are these non-negotiable for architects now?
Because they automate everything. CI/CD, continuous integration, continuous delivery pipelines are the engine of modern software delivery. They ensure every change is built, tested, and deployed consistently and quickly. Removes manual error, increases speed, essential for agile teams.
And infrastructure as code fits in here.
Perfectly. ISC means managing infrastructure through machine-readable configuration files. Code defines your servers, databases, networks. Tools like Bicep or ARM templates for Azure or Terraform for multi-cloud setups.
What's the big win with IAC?
Reproducibility, versioning, infra lives in source control, automation, collaboration. You can spin up or tear down entire environments reliably. It's a game changer for consistency and speed.
Okay, focusing on Azure deployments. Two common choices are Azure App Service and Azure Functions. How does an architect decide?
It really depends on the workload's characteristics. Azure App Service is a fully managed platform, great for hosting standard web apps, RESTful APIs, mobile backends. Think applications that need to be always running, long-running process.
Like a typical website.
Exactly. You get a lot of control, scaling options, deployment slots. Azure Functions, on the other hand, is serverless. It's designed for event-driven and on-demand workloads, short bursts of code triggered by something.
Like processing a queue message or an image upload.
Perfect examples. The big draws are the pay-per-use pricing you only pay when it runs and automatic scaling.
Any downsides to functions?
The main one to watch is the potential for cold starts. If a function hasn't run in a while, there might be a slight delay the first time it's triggered. Need to factor that latency in.
So app service for always-on apps, functions for event-driven, pay-per-use tasks. Watch out for cold starts.
That's the gist of it, yeah. It's about matching the service to the need.
So pulling this all together, we've covered code principles, big patterns, practical coding, data, cloud deployment. It's clear being a .NET architect is way more than just tech skills. The sources really hammer home the importance of soft skills. It's not just what you build, but how you lead and communicate.
Oh, absolutely. Those skills are make or break. Solution design and estimation, turning vague ideas into solid plans and estimating effort. That's huge. Technical documentation, not glamorous maybe, but vital for sharing knowledge and keeping things clear.
Mentoring too, right?
Crucial. Mentoring developers lifts the whole team. And stakeholder communication. That's about bridging the gap between tech and business, managing expectations, getting buy-in. You have to translate.
And making the tough calls.
Yeah, decision-making and trade-offs. Architects constantly weigh options, balance priorities, understand long-term consequences, and crucially, explain why a decision was made. Plus, understanding agile ways of working is just table stakes now. These skills are how an architect actually guides the team and delivers value.
Wow. Okay, so this deep dive really shows the breadth and depth of the .NET architect role, from solid principles deep in the code all the way up to cloud strategy and stakeholder meetings. We hope distilling all this information gives you, our listeners, a much clearer picture and maybe even a shortcut to understanding or stepping into this kind of role.
Definitely. And maybe a final thought to leave you with. The true measure of a great .NET architect isn't just mastering today's tech, though. That's important, of course. It's really about that relentless drive to keep learning, adapting, and figuring out how to strategically apply principles and patterns, both old and new, to the challenges that are coming next, the ones we haven't even fully seen yet. That adaptability is key.